So today, well, the talk of today will be about estimating the reliability of deep neural network regarding permanent faults on GPU devices. I am going to basically summarize somehow the research activities that I carry out during my PhD here at DAUIN. So the outline or the agenda for today will cover 4 main parts: an introduction, a background about graphic processing units, and general reliability of semiconductor devices, how we evaluate reliability on neural networks, and then I am going to talk about which methods can we use to improve these evaluations, the evaluation methodology of DNNs regarding permanent faults, experimental results, a brief explanation about it, conclusions, and future works. So let me start reminding a little bit about the history of GPUs. So GPUs originally were developed for dealing with multimedia applications, gaming, and things like that. But recently, some years ago, they started becoming a big device, a big accelerator for different kind of applications, especially artificial intelligence, for training, for inference, all these things. So nowadays they are more important in applications that are considered safety critical, like for example autonomous driving system, robotics, space, and all of these scenarios. And one of the main characteristics of GPUs is basically the degree of parallelism that they can provide. So they are basically composed of multiple processors that are able to compute several operations in parallel, with a characteristic which is using the single instruction multiple thread. It means that basically there are multiple parallel executions that can have independent control flow, let's say, of each other. And inside the GPU we can have several parallel processors that performs integer floating point operations, special function operations, and also a matrix multiplication accelerator, which are very important for machine learning applications. This evolution, or what allows to have such amount of hardware inside a single chip, basically responds to the continual evolution of semiconductor technology, in which we have high density amount of transistors in a single chip, and especially this permitted to have very powerful application nowadays, like for example high performance computing, artificial intelligence, 5G, and all of these things. And one of the examples is like nowadays a GPU device can have more than 21 billion of transistors, like these examples that I'm presenting here. But well, not everything is as good as it's supposed to be. I mean, I know that the GPU semiconductors can have very great powerful, and we can have a low power consumption, but there are also reliability concerns about it. And these shrinking transistor capabilities, let's say, bring also some problems regarding to some defects or problems that can arise into the chip. And I mean, GPUs are not the exception to suffer these kind of effects. And there are big companies like Google or Meta that have faced several problems regarding to this in their data centers, in which even the chips, after exhaustive tests, are not able to, these tests are not able to detect any defect, and at the end, in the final application, there are some failures that, well, really affect the operational life of the applications. There are 2 different scenarios in which these effects may appear during the manufacturing process, let's say manufacturing defects, material stress, new materials to implement new devices, test escapes, and also we can have defects that may appear during the operational life of the device. Maybe the accelerator wear out or aging, environmental hardness, the temperature is one of the key parameters that may affect the reliability of a chip. And not all of these faults crash the system, like stop the device working. Some of them may silently propagate during the operation of the chip and may produce errors that finally can endanger the application by itself. So considering that GPUs are also susceptible to this kind of faults, and nowadays that we have very heavy workloads like neural networks, deep neural networks, If we consider a safety critical case like, I don't know, an autonomous system that relies on these applications, so a fault in the GPU may induce errors at the computational level of the DNN, and at this level it may produce some catastrophic results. So maybe we have an autonomous system, a crash that may lead a loss of human lives, of these kind of things. Also, in this safety critical system, there are some strict safety standards that demands to devise or design specific countermeasures to these faults. But in order to design effective solutions, it's important to assess in an effective way which are the most critical parts inside the device, inside the GPU, and how we can face this kind of situations. So here, usually how the reliability of neural networks is carried out normally. So basically corrupting at application level the weights or the neuron corruptions, but here there is a problem, and it's these levels of error injections are not able to describe actual faults at the chip level, so they are not realistic at all. So we cannot be sure how much we are describing at that level. There are more accurate scenarios in which we have an RTL model of a chip, let's say of a GPU model, and on top of it we run the application, the neural network, injecting defects inside the gate level, for example, description of the circuit. But even though this is very realistic, the evaluation, very accurate, then we have the problem that it's unfeasible in terms of simulation time. It could take, just for this example that I am presenting here, more than 10,000 days for evaluate just some thousands of faults in the real workload. So alternative evaluations or alternative methodology we have to consider, and this is what I am going to just briefly summarize here. So, as the hardware-software interaction, when we have a neural network, including a GPU device, or it could apply also for other devices, is that there is one part of the hardware in which the defect exists, but this defect will be visible at the software level, basically at the instruction level by somehow a corrupted operation of an instruction. So in this case, some of the faults that the hardware by itself masks, that they don't manage to reach system failure, for example, are neglected. So in this case, a method that is called hardware injection to program transformation basically is software level error injection that take advantage of the real device in order to corrupt the application, use the same device to propagate that possible effect, and to see what happened at the end of the application. So taking this in consideration, I adapt, or basically propose how to model these permanent faults at that level. There are some works that they try to evaluate transient effects due to radiation phenomena, these things, but not at all actual permanent defects in GPUs that induce these soft errors. So the idea here is simple. Basically intercept the assembly level of the kernel of the GPU that is executed right before the execution, insert some specific functions that will corrupt some instructions or specific instruction according to the hardware that I want to target as a faulty, then compile that kernel and then execute in the real device to propagate the fault. During my research, I developed specific saboteur, let's say, functions that allow me to model these faults or errors at the software level in the raster files, integer unit, floating point units, special function units, and recently, well, I also developed an early version for the tensor core units to make these evaluations. In order to assess which is the impact of these errors at this level, there is important to have some observations, let's say. So in terms of neural networks, for image classification applications, I took the accuracy, and I basically adapt a metric that is called relative accuracy degradation, which considers the accuracy of the model of the neural network in a fault-free scenario or golden scenario. And then, after injecting an error or a fault, I calculate the accuracy and calculate which is the difference, the relative difference between them. And based on that metric, I classify every fault that I inject in different ways. So there are some of them that produces device unrecoverable error, which is basically the GPU crashes. Silent data corruption, which means that the neural network seems to compute correctly. but there are some misclassification, for example. In other case, there are no misclassification, and mask, which there are no effects at all. So I performed some evaluation, so I implemented this methodology using a tool based on an available version from NVIDIA that's called NVBit5. Adapting that tool, I evaluate 4 different neural networks: LeNet, AlexNet, RNet-19, BGG16, with different data sets. And here, some of the number of false errors injected at that level, targeting in the first place the raster files, in the second place some of the functional units of one streaming multiprocessor. This evaluation took around 107 hours, which is quite faster than a realistic evaluation, but more realistic than just application level way of evaluate neural networks. Just to highlight the main results that they got, from profiling point of view, the GPU uses the first 10 registers are the most used, let's say, as a destination, as a source, and also they are the most sensitive ones in the terms of fault, let's say, neural network degradation, which is what we see in this place. But in general, the faults affecting the raster files have around 10% of degradation, or induces a 10% of mean accuracy degradation, considering the experiment that I presented before. In the functional units, we have, well, this is just like the main result, and I mean I have more other ways to see these effects, but here what I can see is like the FMAA operation inside the GPU, of course, is the most used one because the characteristics of neural network. And as it is the most used one, it also induces higher level of degradation, up to 20% of degradation in some of the cases. And if we see here, well, I didn't mention that before, but there are 2 types of faults, StuckAt1 or StuckAt0. It means that one of the bits permanently is stuck at 1 or 0, let's say. So for the floating point core, only StuckAt1s are the sensitive ones. When one of the bits of the output operations are stuck at 0, the effect or the degradation is basically, we can neglect it, or it doesn't affect at all the degradation of the neural network. On the other hand, integers are more susceptible in some cases because they are used for thread indexing, for memory access, and these kind of things, so they induce more critical impacts during the general operation of the neural network. So just to conclude, what I am presenting here is effective methodology that allows to evaluate in a more realistic way the impact of permanent faults on neural networks, especially when they are affecting GPU devices. This proposed solution that I just briefly present here target raster files and functional units. And as I mentioned before, raster files, the first set of raster are the most sensitive ones, or are the ones that induces more degradation in the neural network, and as well as the StuckAt1 faults are the most critical one for the functional units, let's say. So of course, this is just one of the initial parts of the research that will allow us to generate or to devise effective hardening techniques that allows to counteract these effects and allows to reduce the degradation of the neural network against these kind of defects. Thank you for your attention. If you have any questions, I am here open for answers.